In this video, we're going to discuss the ionization energy. The ionization energy is defined as the amount of energy required to remove the most loosely bound electron from an atom in the gaseous state in its ground state. So for example, if we had a fluorine atom in its gaseous state, this would be its ground state electron configuration. The ionization energy would be the energy required to move this electron in red. This is the most loosely bound electron, the last one that's added. For neon, same thing. This would be the first electron that we would remove. And for sodium, we would be removing the 3s, so its outermost highest energy electron. So we can remove more than one electron from an atom, of course. The first ionization energy is the energy required to remove the outermost electron to form a +1 cation. So we're removing an electron from a neutral atom. The second ionization energy would be the energy required to remove the second most loosely bound electron from a +1 cation in order to form a +2 cation. Of course, we have a third, possibly a fourth, fifth ionization energy, depending on the element. Another thing about ionization energy is that in order to remove an electron, that process always requires energy. Processes that require energy, we say, are endothermic. Now, the important thing, the thing we want to talk about here, is the periodic trends for ionization energy. The ionization energy tends to increase across a periodic table. It tends to decrease as we move down a group on the periodic table, and it decreases when we start a new period. So you can see if this is my periodic table, the ionization energy tends to increase from left to right across a period. Now, as we'll discuss later, there are some exceptions to this. We'll discuss this in a different video. And as we go down a group, the ionization energy decreases. And if we start a new period, say we go from neon all the way over to sodium, the ionization energy will decrease as we go from neon to sodium and start a new group. So how do we explain these periodic trends? Well, the ionization energy, as you may have guessed, is related to an atom's effective nuclear charge. We know that as we move across the period, the effective nuclear charge increases. So the attractive force that the electrons feel towards the nucleus increases. So the outermost valence electrons, as we go from left to right across a period, the outermost valence electrons, or all electrons, but here we're concerned with the outermost valence, they experience a greater attractive force towards the nucleus. And again, please review the video on effective nuclear charge so that you're clear on exactly why that happens. So the outermost electrons are held more tightly to the nucleus as we move from left to right across a period. So the outermost electrons are held more tightly to the nucleus and therefore require more energy to remove. This results in a greater ionization energy. So as we move from left to right across a period, the effective nuclear charge increases, the electrons are held more tightly, feel a stronger attractive force to the nucleus, and so as we move from left to right, the ionization energy will increase because it takes more energy to remove that outermost electron from the valence shell. Well, what about as we move down a group? We said the ionization energy decreases. Well, as we move down a group on the periodic table, every time we do, we start a new valence shell. This increases the valence electrons' distance from the nucleus, and their effective nuclear charge essentially decreases because they're further from the nucleus, have a less attractive force towards the nucleus. So these electrons are easier to remove as they get further from the nucleus. So these electrons are held less tightly and require less energy to remove, resulting in a lower ionization energy as we move down a period. You can see that here. Again, we're looking at the valence electron configuration. 2s1, 3s1 for sodium, 4s1 for potassium. So the outermost electron, that's the one we're talking about removing, gets further from the nucleus and it's going to be easier to remove. So what about when we start a new period? We said that the ionization energy will decrease. Well, when we start a new period, much as when we go down a group, we're starting a new valence shell. This valence shell is further from the nucleus and will therefore the electron will be held less tightly, but it's also related to the effective nuclear charge. When we start a new shell, that new valence electron experiences a large reduction in its effective nuclear charge because it has a great increase in the amount of shielding, making it easier to remove. Let's look at an example. Here we have neon, atomic number 10, sodium, atomic number 11. For neon, we're talking about removing this electron. This electron experiences a very large effective nuclear charge because there's very little shielding relative to its 10 protons. When we start a new period, or excuse me, a new valence shell for sodium, the sodium 3s electron goes into a new valence shell and it experiences a large reduction in its effective nuclear charge because the number of core electrons increases greatly. It increases from 2 with neon all the way up to 2, 4, 6, 8, 10. And its actual nuclear charge only increased by +1. So this electron in the 3s shell for sodium will experience a large reduction in the effective nuclear charge, making it require much less energy to remove that electron compared to the outermost electron for neon. So be sure you can explain these periodic trends for ionization energy, and be sure you can explain them correctly in terms of effective nuclear charge.